సైకాలజీ ఎవరు చూడు సరే. నాగమణియా? నాగమణియా కళ్యాణినా?
శ్రీనివాసులు.
సైకాలజీ
శ్రీనివాసులు.
శ్రీనివాసులు వి.
అదే
One theorem we have to learn in commutative algebra. If n stands to n, be an R homomorphism
వాటిని రచన
of R modules. F of m stands to n be an homomorphism of R modules. So we have to take here k is equal to kernel f, and h m stands to m by k. We are taking here with a natural R homomorphism. Then there exists a uniform. Then there exists then R exists. There exists a unique R morphism R homomorphism G of m by k. I'm taking here. Then such that F circle GOH, that is condition here.
రాయించాను
అంతే అంటవా?
అట్లా యూట్యూబ్ మొత్తం ఉంటుంది.
అదే ఇందాక నాకు వచ్చే డౌట్ వచ్చింది.
వచ్చిందా?
అదే
M, F, N, H, G, there is m by k. So therefore further the following hold the conditions here. The first condition is on isomorphism if and only if F is on isomorphism.
పక్కన ఈయన విజయ్ కుమార్.
F is on isomorphism if and only they are taking here F is a monomorphism.
ఇది కొత్తదా కాదా అని ఎట్లా తెలుస్తుంది నాకు?
చూడండి పాతదే ఉన్నట్టుంది. విజయ్ కుమార్ వచ్చింది కదా.
F is an isomorphism if and only F is monomorphism. So therefore they are taking the proof here. Clearly we are taking the homomorphism. What is the homomorphism? H n m stands to m by k. M stands to m by k is an epimorphism. So now we have to
ఎన్విరాన్మెంటల్ సైన్స్
m by k g m by k
No,
two
వచ్చింది.
stands. So what we have to take
కెమిస్ట్రీ
it?
రాలే
మోహన్ బాబు వస్తాడు.
G express k
ఆయననే ఆడున్నాడు.
G express k is equal to f of x for all x belongs to m I'm taking here. So therefore if x plus k is equal to y plus k in commutative words we are able to equal to b plus x plus k is equal to y plus k. But x minus y belongs to k is equal to kernel f. X minus y belongs to k is equal to kernel f. So therefore we are writing f of x minus f of y we are taking here. F of x minus f of y is equal to f of this one condition I'm writing here f of x minus y is equal to 0. So, but in the condition of multiplication f of x is equal to f of x into f of xy is equal to f of x into f of y. F of x into f of y is equal to f of xy. So the j is well defined, right? Because in addition process and the multiplication process we have to successful. So we can easily verify that these are homomorphic. But in any x belongs to m, but in any
నేను
x
ఫ్యాకల్టీ
belongs to
ఎవరు ఎవరది?
if any x belongs to m, f of f of x is equal to g of x plus k. We can write here this is also g circle h. So this is also g of x plus k may be written as also g circle h into x we are taking here. So hence we are taking this one we are taking is equal to f is equal to g circle h. But we know that g is equal to m by k stands to n. So but any R homomorphism such that the first differentiate f of g dash of OH g of x plus k is equal to, we know that g of x plus k is equal to g circle h, x is equal to f of x. The first derivative, g of g circle h into x, this is called as the first derivative of g dash of circle h. This is the first derivative I'm taking g circle of g dash circle of h into x I'm taking here. So that is equal to g dash of x plus k. So therefore I'm taking here. So that is x plus k belongs to m by k. So therefore g is equal to also we are taking g is equal to g dash. Thus g is unique that f is equal to g circle h. So therefore also g of x plus k is equal to 0. So therefore
अब काय नहीं थी छोरी रे
g of x plus is 0. Therefore x belongs to kernel f. Therefore x belongs to kernel f. X belongs to kernel f also is
मैं
equal
घाल
to
काय
0.
काय केले दिसो होता है घाल
X plus k is equal to k. Then 0 element is m by k. So then x plus k is equal to k. Therefore the g is a monomorphism. So monomorphism means g is an isomorphism.
हाँ कोणता छोरा रे कोणता नहीं करो पंजाब
G is on isomorphism. G is on epimorphism. So therefore
अंदर से खतरा है कि सब
F is on isomorphism, epimorphism. That is called as on F is an epimorphism also. G, both are G. F is on epimorphism.
2400
So F is equal to G circle H. G circle H and H is epimorphism. And H is
आता नहीं कोनी अब मस्त
and
छोरा काय
H
की
is H is on isomorphism.
हाँ वो पहले तो मोना वो पैसा को जिगला कतरा हाँ 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 कतरा
H is an isomorphism. So therefore H is an isomorphism, H is a
2400 काय
monomorphism.
के करने
So therefore monomorphism.
वो
So
बिने
H is
घाल
a
वास्ता
monomorphism also we can take that kernel H is equal to 0. So therefore K is equal to 0 since kernel H is equal to K. So therefore K is equal to 0, kernel H is equal to K. So isomorphism, monomorphism condition is satisfied, kernel H is equal to 0. Therefore kernel H is equal to K. So therefore kernel H is equal to 0, the condition is satisfied here. F is on monomorphism, we are taking that one. So the importance of this one, any homomorphism can be written as composition of a monomorphism and epimorphism. This can be stated fundamental theorem of homomorphism, but popular of this one, therefore we are taking a homomorphism. So this one, from this theorem, we have to learn also fundamental theorem of homomorphism. Also. Fundamental theorem of homomorphism.
course history paper 8 మొదలయ్యా నాలుగు ఇవ్వాలి ఇవి అడుగుతానే ఉన్నాయి పొలిటికల్ సైన్స్ పబ్లిక్ అడ్మిన్ వీళ్ళందరూ అడుగుతానే ఉన్నారు అందరూ ఇది
Fundamental theorem of homomorphism. Let M stands to n be an R.
తెలుసు అదే మీటింగ్ ఐడి హోస్ట్ ఐడి పాస్వర్డ్
Let M be let M be an R. Let M stands to be R on R. Let M stands to n be so let M stands to n be an R. homomorphism of R modules. R modules. R modules. So then f of m is an R submodule of n and the quotient module m by kernel f of m if f is an epimorphism, then m by kernel f equivalence to n. When m by kernel f equivalence to n, we are taking here. So what is the proof of this one condition I am taking here? So m stands to n be an homomorphism of R modules here. Then m is our submodule we are taking here. So m by kernel f equals to m epimorphism. So we have f of m. So f of m
చూడు వచ్చేసింది అన్మ్యూట్ ఉన్నామా చూడు అన్మ్యూట్ ఉన్నామా
f of x x belongs to m. You can easily check that f of m is an submodule. F of x belongs to m. You can easily check that f of m or submodule. F of m is equal to because is our submodule of n. So therefore, G m by kernel f, G by kernel f is equal to f of stands to f of m. F of stands to f of m. We can take in the G of x plus kernel f. G x plus kernel f is equal to, so G of x kernel f is equal to, we are taking f of x for any x belongs to m, we are taking. Yeah. So therefore we know that x plus kernel f is equal to y plus kernel f. X plus kernel f is equal to y plus kernel f. Then x minus y belongs to kernel f. So that both f of x minus y is equal to 0. So therefore f of x and therefore f of x is equal to f of x minus f of y, that minus y goes to the right hand side, f of x is equal to f of y. So therefore f of x is equal to f of y means G is well defined. well defined. This shows that G is well defined. So therefore, we can check that G is on R homomorphism. R is homomorphism since an element of since f of m is one of the form f of x is equal to G of x plus kernel f. G of x plus kernel f for x belongs to m. X belongs to m. We are taking here the following G is onto. So how it is onto G of x plus kernel f we are taking here is equal to 0. Therefore, f of x is equal to 0. So therefore, x belongs to kernel f. That is x plus kernel f is equal to kernel f. X plus kernel f is equal to also we are taking here kernel f. But 0 element we are taking here m by kernel f. That is, so G is on a monomorphism and hence monomorphism is satisfied, well defined. Homomorphism. So both the conditions are satisfied here. G is monomorphism. Hence, these two conditions is satisfied in here from the earlier theorem. So isomorphism and monomorphism. Isomorphism is also condition satisfied here. Therefore, m by kernel f equivalent to f of m. So that's on to. So therefore, f of m is equal to m. Therefore, m by kernel f is equal to also equivalent to m. The condition is satisfied. Direct sums and direct products. We can today the direct sums and direct sum products. So we can take direct summons first of all. Direct summons, and the direct commands here. The direct summons, direct sums, direct products. So the product means is a multiplication. What is the direct summons here? We learned the earlier fundamental theorem of homomorphism. Fundamental theorem of homomorphism. M by kernel f equivalent to the n. We know that. So mastering. So this one we introduced the concept in the summand also. Obtain necessary and sufficient conditions submodule also. So before direct summand, submodule before sum, you can take the submodule before become a direct summand. So let one theorem we have taken here direct summand here. Let n and k submodules of module. Let n and k submodules of m submodules of m module m over a ring R m over a ring R. Then the following hold n by n intersection k is equal to n plus k by k. If n subset of equal to k, then m by n by k by n. M by n k by n is equal to m by k. Both the n's are cancelled here. So both the n's are cancelled here. So therefore m by k. You have to prove these two one. Proof by the fundamental theorem of homomorphism. We know that here m by kernel f is equal to n. So therefore, we have to exhibit the homomorphism of n onto n plus k by k. We are taking here whose kernel is n intersection k. So therefore, f of n stands to n. We are taking here f of n stands to n. That is f of n stands to n means n plus k by k. But we know that f of x is equal to x plus k. We know that f of x is equal to x plus k for all x belongs to n. We are taking here. So clearly R is an homomorphism. So we have to prove onto means one we have to, but then only we can onto here. So z plus k belongs to n plus k by k. So therefore z belongs to n plus k. So n plus k, z belongs to n plus k. We know that here. So we can write here z is equal to x plus y. So therefore x belongs to n and y belongs to k. X belongs to n, y belongs to k. We are taking it. Hence f is apomorphism. Hence f is apomorphism here. So also since k is the 0, and also k is the 0 here, n plus k by k. So kernel f is equal to x belongs to n by f of x is equal to k. So x belongs to n by x plus k is equal to k. X belongs to n by x belongs to k, that is n intersection. X belongs to n, x belongs to k is equal n intersections with n. We know that the fundamental theorem of homomorphism and of the earlier theorems also, n by n intersection k is equal to n plus k by k. So that is equivalence to n by n intersection k is equal to n plus k by k. That's the second condition we are taking here. The second condition we are taking is, suppose n subset of equivalence to k. So therefore k by n, x plus n by x belongs to k. X plus n by x belongs to k is a submodule of the quotient module. The quotient module m by n is a submodule of the quotient module m by n. You can take here g m by n stands to m by k. We are taking here. Therefore, g of x plus n is equal to, we know that x plus k. So g of x plus n is equal to x plus k for all x belongs to m. For all x belongs to m, we know that. So we can clearly, g is on epimorphism, g is on epimorphism is equal, kernel g is equal to x plus n belongs to m by n by g x plus n is equal to n. We know that this condition, but we have to write here x plus n by x plus k. X plus n by x plus k is equal to also k here. So therefore x plus n by x belongs to k also is the k by n. So x plus k is equal to k means x belongs to k. We know that that for fundamental theorem m by n by k by n, this is should cancel here. That is m by k of the earlier of now I have told you. So here for any ring R, the Cartesian product of R into R we are taking here can be viewed as an R module, which is the submodules of R into 0 and the 0 into R have a distinguished role. Every element of R into R we are taking by unit written as x1 plus x2, x1 plus x2, where we are taking here x1 belongs to R into 0, x1 R belongs to R into 0 we are taking here, and x2 belongs to 0, then R into A comma B, A0 plus 0b. A0 plus 0b we are taking the characterizer submodule of module. So then we have in general we have taken the above property, the condition is satisfied here. Let M1, M2, M3, and so on in mind. The submodules submodules of on R module. The following are equivalent. equivalent. So the first condition m is equal to m1 plus m2 plus m3 and so on plus mn. So mi intersection subset of j not equal to 1, that is mj is equal to 0 for all 1 less than or equal to I less than or equal to, then the first condition. The second condition, every element of m can be uniquely determined x1 plus x2 plus x3 plus xn. Xi belongs to mi. There exist endomorphisms. There exist endomorphisms P1, P2, and so on, Pn of such that Pim, Mi, P1, P2, and so on, Pn is equal to IDM. Therefore, Pi circle Pj is equal to 0 for all I not equal to Pi circle Pj. For I not equal to j, we are taking a mistake. The first condition to second condition to third condition to first condition we have to prove here. Then 1 to 2. Then equal to m1 plus m2 plus m3 and so on. M1 we have taken here that every element of mb is uniquely x1 plus x2 plus xn. X belongs to 1 to 2 we are taking here. Summation of I is equal to 1 to n mi. In the mi intersection, summation of j not equal to 1, mj not equal to 0. For m is equal to what we have taken here. From m is equal to summation of I is equal to 1 to n. I is equal to 1 to n. Mi, I is equal to 1 to m. Mi follows that every element n can be written. Every element n can be written as we can write here x1 plus x2 plus x3 and so on. Xn, which xi belongs to xmi. So x1 plus x2 plus and so on plus xn. Then y1 plus y2 plus and so on plus yn. So x1 plus x2 plus xn. So we know that the mi intersection summation of j is not equal to m j is equal to j. So therefore we have to take with xi yi belongs to mi. So then 1 less than or equal to I less than or equal to xi minus yi. Summation of j not equal to 1. It is yj minus xj. It belongs to mi intersection summation of j not equal to 1. You know that mj not equal to mj is equal to 0. But even though, so therefore these conditions are satisfied here. Where their condition here xi minus ya summation of j not equal to 1 yj minus xj. That means it is belongs to mi intersection summation of j not equal to mj is equal to 1. Hence xi minus y is equal to 0. Therefore xi is equal to yi for all 1 less than or equal to I less than or equal to m. So the condition is satisfied here. 2 is equal to 3. Suppose m1 plus m2, x1 plus x2 plus xn, then m1 p1 plus p2 plus and so on pn equal to idm. I not equal to j. So 2 is equal to 3. Suppose every element of M can be unequally x1 plus x2 plus and so on plus xn. So with xi belongs to mi for any 1 less than or equal to I less than or equal to n. So we can define here Pi m stands to F. Pi instantiation taking there. Pi x is equal to xi, where x is equal to x1 plus x2 plus x3 and so on plus xn we are taking here. That is xi belongs to F. So clearly Pi is R module of homomorphism of M into itself. Therefore Pi is an endomorphism also. We can know that Pi is an endomorphism of M. Pi is an endomorphism of M we are taking here. So therefore xj belongs to mi. Xj belongs to mi mj and pj xj. Therefore pj xj is equal to xj. So therefore f of pj of m is equal to mj. So what we know that pj, so px is equal to xj, xn x plus xn plus x2 plus xn. xi belongs to mi. We can take that R module here. Therefore we know that pij is equal to mi. So therefore P hence Pjm is equal to Mj and Pjxj is equal to Xj, that's the one. So therefore here for all one less than or equal to j less than or equal to x is equal to x1 plus x2 and so on plus xn belongs to m, that is xi belongs to m I. So therefore the condition is x. Yeah. P1 plus P2 plus and so on plus Pm x. So therefore summation of and I is equal to 1. Pj of x we are taking here. Summation of I is equal to 1 to n we are taking here. That is xi is equal to Pix is summation of xi is equal to x. So therefore plus we are taking here P1 plus P2 plus P3 and so on plus Pn is equal to idf. So therefore x is equal to x1 plus x2 and so on plus xn belongs to m. That is xi belongs to mi. So therefore Pi circle Pj into x. Pixj, Pixj is 0. Y belongs to I not equal to 0 condition we are taking here. So therefore in this condition we are taking here Pi circle Pj I am taking here, that is 0 for all I belongs to, for all I not equal to 0, for all I not equal to 3 to 1 I am taking here. So for suppose I am taking here P1, P2, and Pn. P1, P2, P3, P4, and up to P1, P2, P3, P4, P5, P6, and up to Pn belongs to end or n. Pn we are taking here end of Rm such that P1 is equal to know that M1 P1 plus P2 P1 plus P2 plus P3 plus P4 and so on. Pn is equal to IDM and Pi circle Pj is equal to 0, but it is not condition of equal to I not equal to. First we know that for any I Pi of all we are taking or taking a Pi circle, that is summation of j Pj, summation of j Pi circle Pj PI circle PJ we are taking here. PI circle PJ. For any x belongs to we are taking here. PI x belongs to PIM equal to MI, that is x is equal to P1 plus P2 and so on plus Pn x, P1 x, P2 x plus Pn of x belongs to M1 and so on plus Mn. So P1 x plus P2 x plus P3 x plus so on plus Pn x belongs to M1. So there we are taking here plus M1 also the last condition here. So first M is equal we are taking here. First M is equal to, we know that M1 plus M2 plus M3 plus and so on plus Mn here. For any we are taking here 1 less than or I less than or equal to n. So therefore xi belongs to n. So xi is equal to Pix for some x belongs to n we are taking here. And hence we are taking here Pix is equal to Pi circle Pi of x. So this Pi of xa we are taking that is equal to xi. So Pi circle of Pi is equal to x, that is only one Pi is equal to x, that is xi. So Pi is indicated on Mi. So therefore it is indicated on Mi. 1 less than or equal to I less than or equal to n. So therefore xi is equal to summation of j not equal to 1 xj with xi belongs to mi and xj belongs to j, that is j not equal to y we are writing here. So thus we are taking here j not equal to y. So therefore xi, pi of xi, pi summation of j not equal to 1 j xi. So that's the summation of j not equal to 1. What is the condition here? P circle of P circle of ij into xj. P circle of P circle of phi, P circle of phi, Pi circle of Pj into Fj is equal to 0. We know that the value is here. So therefore, Mi intersection summation of J not equal to 1. J not equal to 118a if that value is with the comma. This is so therefore that is 0. So we have here that NNK are submodules here. A module M over heading R following equivalents of each other. What is the following of equivalents so that we have to see here? M plus k is equal to m and n intersection k is equal to 0. Every element of m can be uniquely can be written as x plus y. If x belongs to n and y belongs to k. See here, every element of n can be uniquely written x plus y and x belongs to n, y belongs to k. So there are endomorphism of p and q, such that we are taking a endomorphism of p of n is equal to n, and q of n is equal to k. K of n is equal to k. K of n is equal to k. Therefore, p plus q is equal to idm. So therefore, p of that means p circle of q is equal to 0. So from this one, its consequences of q circle q is equal to 0. So therefore, P is equal to Q circle of IDM is equal to Q circle of ID means P plus Q is equal to. We can write this condition as Q circle of P and Q, and Q circle of Q. I'm dividing this one Q circle of this one. So therefore, Q circle of P plus IDM. IDM means Q of Q is IDM of P minus P and 0 circle of Q. So therefore, Q0 P, Q circle of P minus Q circle of Q is equal to Q circle of P as I'm writing here. Q circle of P as well I'm writing here. then Q. Why? Because this is only P circle of P. There is no P circle of Q here. Then Q circle of P is equal to 0. So therefore Q circle of P we are writing here. So therefore Q circle of P is equal to 0. We can state the condition here. Definition. Let M be R module a submodule N of M is said to be direct command of M if there is a submodule of K, So therefore, it's just a direct command. Direct command is that some the submodule of K you can take here M such that K of M such that M plus K is equal to M we are taking here. And in intersection K is equal to 0 for any one of these two conditions here. In this case, we have to say that M is the internal direction. M is the internal direction we are taking here, and the N and NK and N and K dash, and denote this by writing, and denote this by writing M is equal to M plus K. M is equal to M plus K. K is said to be direct complement of M. K is said to be direct complement of N. So therefore, if the complement of M we have taken is M1, M2. If we are taking here M1, M2, M3, and so on, Mn or submodules or submodules of a module, M satisfying anyone, here of the conditions of this one. So means internal sum of what is it? M1, M2, and so on, Mn. But denote by writing here M is equal to M1 plus or minus M2 plus or minus plus or Mn. M1 plus M1 plus M2 plus Mn. Or M is equal to summation of I is equal to 1 to N plus Mi. So if this is called summand, the summand, then note this command are not the unit. So we can take one example here. Let R be anything, N is equal to R into R. Then R is a submodule under the usual operation. Then M is on R module under the usual operation. N is equal to know that X comma Y. That is R into R, that is equal to X into Y. K is equal to X to 0. X belongs to R. L is equal to 0, Y, and Y belongs to R. So here X comma Y and X comma 0, 0 comma Y, Y belongs to R. Then any X comma Y belongs to R. So therefore we have to take here X comma Y belongs to, and we are taking here X comma Y is equal to Y comma Y. I'm taking here plus X comma Y minus 0. I'm taking the above condition X Y Y, then X minus Y is equal to 0 is equal to We are writing here that is x comma x plus 0 comma y minus x, again the negative. That is x comma 0 and y comma 0. 0 comma x comma 0 and 0 comma y, therefore the value is 0. So therefore hence n plus k is equal to m and is equal to n plus f. I'll command this one. This is a command, but this is n plus k is equal to m, n plus l is equal to the command of k plus l. We are taking here also clearly n intersection k here, k intersection l is equal to l intersection. All the values is 0. All the values is 0. So m is equal to n summand k, n summand l, k summand l. So therefore, n is the direct amount of k and L are the both direct complements here. So we are taking here. N is the direct amount and k and L are comparable here. So we are writing here k subset of L or L subset of k. We are taking here the direct complements of N. You can even take the k is equal to L. So therefore n plus k is equal to n plus L. N intersection k is equal to n intersection L. So then we have k is equal to k plus n intersection k. So k plus n intersection L we are writing here. So k plus n intersection L. So that we are maybe change as k plus n intersection L. That is equal to L we are taking here. Then another small another one here. Let n be a direct summand of an R module M and K, a direct complement of M. So M by K equivalents to N, M by N equivalents to K. M by K equivalents to N, M by N equivalents to K. That is here. So since we know that the direct complement of N, we have N is equal to M. If we know that N is equal to M, then the K intersection N is equal to 0 also we have known that. So M by K is equal to n plus k by k. We know that of earlier theorem that k by n intersection n, so that is equal to n by 0 is equal to n, that is equivalent to, so therefore n by n is equivalent to k. This is one we have to do. Then direct sum. There is sum also. Now we have to do direct sums. Direct sums we are taking here. So you learn the concept of the earlier direct sums of the finite number and submodules. So we have to take the external direct sum on the whole establishing. The definition of the direct sum is extended on arbitrary to finite or infinite of plus modules. We have taken the categorical definition of direct sum here. So what is the definition of the direct sum here? Let I belongs to I. Let M by I belongs to I, the class of modules. Be a class of modules. Be a class of modules over a ring R. F a M of Fi by I belongs to J is said to be a direct sum of you are taking here Mi by I belongs to Y is the following are satisfied here. Is the following are satisfied here. M is an R module. First one is M is on R module. M is on R module. Each I belongs to Y. That's why Mi belongs to an homomorphism. M is R module GI. Mi stands to n. I am taking here, and R is a homomorphism here. R is homomorphism here. Homomorphism here. So for all I belongs to J, for all I belongs to J here, there exists a unicorn homomorphism G. M stands to n. G circle of f of I GI for all I belongs to Y we are taking it. So what is the condition of G M extension such that GI circle of f of I for all I belongs to Y we are taking here? That is the condition we have to write here. That's one. This one. So we have direct sum as given our modules here. It is limit we have to learn here. Then another one theorem we have to learn here. Another one definition we have to learn here. For any R modules, we are taking here M1, M2, M3, and so on. Mn taking here by the direction, the direction we are taking M1 into M2 into and so on. Mn. Sometimes is called the extremely direct sum of M1, M2, and Mn. We denote here that is phi I is equal to 1 to n. Hence, it's Mi we are writing here this one. Let M1, M2, M3, and so on. Mn we are taking here. This is isomorphic with we are taking the product here. M1 by multiplication, the sum and is over. Then is the product we are taking here. M1, M2, M3, so on. Mn here. G is equal to also M1, M2, into and so on. Mn here stands M taking here. Beyond isomorphism. K is equal to x1, x2, and so on. Xn belongs to Mi into M1 into M2 into Mi. K equivalents to M. K1 plus K2 plus summand this one plus Kn I'm taking it. The summand equal to M1 into my product here, M1 into Mn here. So Mi G of K of I. So this can be easily verified that N1, N2, and so on, N3, Nn are submodules of N comma Ni is equivalent to Mi here Therefore, where 1 less than or equal to I less than or equal to. So the condition is very easy. N1, N2 is submodules, therefore Ni. So we can take that Ni equivalence to Mi, 1 less than or equal to I less than or equal to N. The condition satisfied here. What we are writing here, N is equal to N1 summand plus N2 summand plus N3 summand. And that means addition, summation of plus and so on plus N. So conversely, we have to conversely we have to take conversely we have to conversely suppose N1, N2 and N, the submodules N1, N2, N are submodules. Sir. R submodules here. M into M comma M comma N M comma Ni is equal to M comma Ni. So and M is the internal. The and M is the internal here. M is the internal direction here. And M is the internal direct sum here. So therefore N1, N2, N3, N4 and so on Nn. N1, N2, N3 and so on. Nn we are taking here. So therefore let F1 M1 Mi to Ni. So Mi F of Fmi to Mi, Ni, sorry, Mi to Ni. So therefore there is the homomorphism of I. Therefore Ni subset of Mi, Fi can be considered here. Fi can be considered R is an homomorphism. F is an homomorphism of Mi. So therefore N is a R module. N is R module here. Mi stands to N. We are taking here. R is homomorphism. Defining G stands to Mn. As follows: X belongs to M. X can be uniquely written as X equal to X1 plus X2 plus X3 and so on plus Xn. Which Xi belongs to Ni. Which Xi belongs to Ni I am taking here. So G of X is the defining here. Summation of I is equal to 1 to N. Gi Fi inverse of Xi. Fi inverse of Xi. So it can be easily verified here. G of M stands to N is the unique homomorphism of G circle F of I is equal to Gi for all. G circle F of I is equal for all G of I. For all 1 less than or equal to I less than or equal to N condition satisfies here. So third M here. F of I 1 less than or equal to I less than or equal to N satisfies 1 and 2 of this one. Hence is actual direct sum of hence is the by M is the external direct sum of M1, M2, M3, M1, M1, M2, M1, M2, M3, M4, M5, and so on Mn. If Mi if Mi if Mi belongs to any class of if any R class of R modules here, M of f of I belongs to I am taking here. So direct sum of mi is here in the following. So we have to prove the apomorphism and also homomorphism here. So fix is the necessarily homomorphism. That means injections here. Injections also. Therefore, hence each mi is isomorphic with submodule of m also we are taking here. Now we are taking here direct product. Direct products also I'm taking here. So in the direct process, so we introduce that we then introduce it another concept, the direct product of a given class module over a ring R. The definition of this concept is also unlocks that direct sum given here they except the taking homomorphism in the same in the reverse direction. The precisely takes simple the Cartesian product of a given class module. We introduce the categorical concept of the direct sum. The products also we have to take here multiplication the definition here. Let R be a ring and mi I belongs to I be a class of R module. A pair M P I belongs to J is said to be a product of mi by I belongs to I. The following are satisfied. What is the following conditions of we have taking here mi belongs to? So the R is a model, we know that I belongs to I. That means small I values in the big I, the values will be there. So therefore, the first condition is M is on R module for each I belongs to I. Pi that is M stands to Mi. So is on R is homomorphism. R is homomorphism we have to take here. The second, these two conditions are satisfying here only. Then if n is on R module, if n is any R module for each I belongs to I, we are taking here. I belongs to n, Qi belongs to Qi, that is n stands to M1, we are taking here. So is an R homomorphism we are taking it. Then there exists a unique unique or homomorphism we are taking here. That is Q stands to M such that Pi circle of Q, that is Pi circle of Q is equal to Pi we are taking it, that so we are writing this condition. So we can take in the diagram of this one here. See M Y Pi. This is it. So this is the fundamental of this one. I'm not the visual. This is the direct product of the given class of R, the module here. Consider let R be a ring. I belongs to J. Be a class of R module. When the direct product I belongs to J exists and necessarily and essentially and existent in essentially unique in the following unique in the following unique the following sense unique in the following in the sense we are taking here. Yes, we were saying. Let's say if m that is I belongs to I, m dash pi dash I belongs to I, like the direct product or direct product mi by I belongs to I, when n equals to m dash, and the same as isomorphism m to m dash, such as p dash p is equal to pi, so that is pi. So for all I belongs to for all I belongs to I, we are taking here. For all I belongs to I, we are taking here. Here dash m1, that is pi, this is p, pi dash p. So pi dash means that is circle of p is equal to p. So this is a fundamental, this is the given, this is the given, this is the given for statement. Now we can do that. Let m be the usual Cartesian product. Let m be the usual Cartesian product. My dash is my dash is m is equal to x to y. Union of I belongs to I means I value is there. So therefore x of I belongs to I mi. So therefore for all x for I belongs xi belongs to m, for all I belongs to j, for I belongs to small I belongs to small I belongs to capital I, we are taking here. So the m is an R module we are taking here. Then m is on R module under the usual operation, operations we are taking here. Under the usual operations we can define any x comma y belongs to m, k belongs to R, x plus y into y, xi plus yi. So therefore ax into y is equal to ax into x into y is equal to ax, and taking the common. For all I belongs to j, we are taking here. For all I belongs to I am taking here. So this one for all I belongs to, we begin here pi is equal to m stands to m. So pix, what is pix is equal to xi. So we know that x for all x belongs to m, pi is the R homomorphism. We shall verify the condition by the satisfied here m of earlier theorems of pi. I belongs to y, we are taking it. The pi is in different brackets also we are taking here. So let us know, let us n be on R module, let n be let m be in our module, and for each we are taking here I belongs to I, n comes to mi on R homomorphism, then define 2 n stands to m as follows for y belongs to. So therefore q of y, the qi into y for all I belongs to I here. Now you can easily verify that who is the only R homomorphism is on a homomorphism L into n into such that a circle q is equal to qi for all. So we are taking this one here. Why we are taking let n be any submodule I belongs to qa is because we know that a n stands for mi is on homomorphism. But even though q stands for mi, y belongs to q of y. So q of y is equal to I, then q of y, q of y, small I belongs to capital I, we are also q small belongs capital I. But we can verify a homomorphism PA circle q is equal to qi for all small I belongs to capital. That means in capital I there is a small value is there. So for thus we are taking here thus I belongs to I. The direct product of mi by I belongs to I. So to prove uniqueness, so m of p of I, that is I belongs to I, then m of p of I, that is I belongs to I, the direct product. This is a direct products we are taking here. So take m dash to be n, m dash to be n, and pi dash to be qi. So to get a homomorphism, to get a homomorphism we are taking here. P dash equivalence to m dash here. By taking P dash to m dash, that is of Pi circle of P dash, that is also Pi dash. So Pi circle of P dash is equal to Pi dash for I belongs to I, we know that here. So therefore, be interchanging the roles and m dash here. M and M dash here. We get our homomorphism. We take here P M to M dash such that Pi dash OP is equal to P for all I belongs to I. We can take here. Now any I belongs to I, we can take here I belongs to I. We are taking here. Then we can take the diagram here. See here, this is the diagram in I belongs to I. So we can take here. So P dash circle of P dash OP. So Pi O dash circle of P dash. I'm saying circle of associate that one. So Pi dash P is equal to Pi. We are writing that Pi is equal to all n. This we have to write here. Now we take here. Now we take here m for n and Pi for Qi. We are taking here. So by this uniqueness, we get that P dash OP. IDM. So similarly, we get that P dash OP is equal to IDM. Thus, P is an homomorphism of M1 onto M is onto then M dash P dash OP is equal to Pi for all I belongs to I am taking here. So therefore, if M, therefore Pi, that is I belongs to I, so taking a direct product of Mi, I belongs to I, we simply say that M is the direct product of Mi. M is equal to I belongs to J. Mi. So this condition is satisfied here. And another theorem we have to learn. Let M by I belongs to Y. I belongs to I. Be a class of modules. Be a class of modules. in the direct sum of these, in the direct isomorphic submodule of the direct product. If it is finite, say I is equal to 1, 2, 3, 4, so on, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on, yeah. Then the direct sum product. The direct product also we are taking here. M1, M2, M3, and so on, Mn are the same and equal to the Cartesian product. That Cartesian product, that what is the Cartesian product? The multiplication. M1 into M2 into M3 into so on, Mn. So this is also we have to learn the earlier theorems of the proofs of the same, the Cartesian products of the proof of the same, this one. Yeah, this one theorem we have to learn here today. Suppose we are taking here. Suppose we are taking here M of I belongs to I. We are taking here the direct product of class I belongs to I is arm of our modules we are taking here. Of our modules we are taking here. So therefore, fact of I belongs to I is an epimorphism. Epimorphism means homomorphism. That's all the conditions. M is an onto condition taking here. Onto condition taking here. So therefore, Mi and Ni is equal to kernel Pi we are taking here. So following goal. So first one M by Ni equivalence to Mi. I belongs to I. Second condition, intersection of I belongs to I. Ni is equal to 0. In third condition, Ni plus intersection of j is equal to 1. When j is equal to m for all I belongs to j. I belongs to I. We are taking here. I belongs to I. We are taking this one also. So what is the proof here? The proof here. So let n is equal to the Cartesian product. We know that mi's and for any I belongs to I. We know that here. So defines qi that means n stands to mi. So therefore qi of x is equal to x of I. So therefore x of I, we know that here qi is a homomorphism. So therefore qi is a homomorphism here. N of q of I, that is I belongs to I. We know that. The direct product of Mi. So this one isomorphism of when I say isomorphism, Q of M stands to. So Pi circle of Q is equal to Qi for all I belongs to. So we can easily observe that here each of Qi that I belongs to I. The surjection of the surjection and hence surjection. Therefore, hence there surjection is there. Suppose surjection is we can doing here. So hence so is Pi. So Pi is an apomorphism. Apomorphism is an apomorphism for all I belongs to I. We are taking here that Ni is equal to kernel of Pi, kernel of Pi, kernel of Pi we are taking here. So by the fundamental theorem, homomorphism by kernel F is equal, we know that here. So M by Ni is equivalent to Mi. So that is I belongs to I, we know that here. To prove that X belongs to intersection of I belongs to I, Ni, so Pix is equal to 0 for all I belongs to I also we know that. So consider the element, what is the consider of the element here? Q inverse of x in n we are taking here. This is also I belongs to I we are taking it. Now we are writing this one fundamental formula. P inverse of x into I. Pi circle of Q, that is P inverse of Q. I'm writing this is the P inverse of circle Q. That means Pix is equal to 0. The condition is 0 here. So hence we are taking here Q inverse of x is equal to 0. So hence x is equal to 0. Therefore Q inverse is on isomorphism. Isomorphism here. So intersection of I belongs to y, Ni is equal to 0 here. To prove that here, let we can take here I not belongs to I. So x belongs to m, we can take here. Let y comma z belongs to n, such that y of I, q of inverse of x 0, I not equal, I not equal to I not equal to 0, I is equal to I 0. So this is the another one we are taking here. And z of I is equal to, we can put 0 of q inverse on x. So again same here. Again we are repeating q inverse 0, we are I not equal to I 0. This is one, that I is equal to I naught. Medium rasam q inverse x, so I is equal to I naught rasam, q inverse I is equal to I naught rasam. Middle 0 is equal to I is equal to I naught rasam, then in the one z is equal 0 is equal to I is equal to I naught rasam. But then we have taken here, but then qi naught y, yi naught y is equal to 0, or I not equal to I naught. So therefore QIZ is equal to ZI is equal to 0. So the condition is hence Pi naught Qy is equal to 0, and Pi Q of Z is equal to 0 for all I not equal to 0, which implies that Q of Y belongs to Ni naught. So Q of Z belongs to intersection I naught equal to net. That is n. So what is the belongs to here? Qy belongs to Ni naught. Qz belongs to Ni intersection of I naught. So both this is the intersection. That's why the condition here, since we are taking here y plus z is equal to Q inverse of x. So therefore x is equal to Q of y plus Q of z belongs to Ni naught plus intersection of I naught and Ni. So this is the complete of this one. So the condition what intersection Q inverse I not equal to not equal to yi. So by Q inverse x x I not equal to zi, but in yi 0 I equal to I naught, in zi I equal to I naught. The condition is satisfying Q y equal to n I naught to z belongs to intersection I naught to Ni. Therefore x equal to Q y plus Q z belongs to n I naught plus intersection equal to I naught n of I. This is a complete set. Any doubts? Ask me.